So we said in the last video that we're going to look for the f double derivative of x, and we're also going to look for the Jacobi accessory equation. So let's start off with the f double derivative of x. We're going to find the Taylor expansion. Now this is a recap, and you can have a look at the video on the Taylor series if you're unsure about this. But let's say, for example, we've got a function here f of x, and we have a point here x, so that's going to be the point f of x, and we pick another point x plus epsilon, and this point up here is going to be f of x plus epsilon. So what we want to do is we want to approximate, or we want to find this distance here. So the distance here is going to be f of x plus epsilon minus f of x, so that's this distance. Now by the Taylor expansion, this distance here is going to be given by epsilon times f derivative of x. So you can see this intuitively is going to be the gradient at this point here times the distance, which is going to be epsilon, and that's going to give us this small height here. Okay, so from this point here to this point here, but that's going to be our first approximation, and it's not going to be the full distance. So we can add on then our second approximation, and it's going to be given by epsilon squared upon 2 factorial times the second derivative. Of course, it's not going to give us the exact value. We would have to add on the further values, that is the third derivative and fourth derivative, and so on and so forth. So I've just lumped those all together in this term here, which is the epsilon cubed. So this is our Taylor expansion, and again, if you're unsure of Taylor expansion, check the video out at the start of the series. But we're not looking for the Taylor expansion of a simple function, we're looking for the Taylor expansion of a functional. So we have to try and relate these terms here to our actual functional. So our f of x here will be replaced by our functional, which is going to be f of x, y derivative. So we're going to use this form here for our simple functional. Now adding on the epsilon here, well, in terms of our functional, what we're going to do is we're going to add on our variation. So we add our variation onto this here, and the functional with a variation added on is going to be given by f of x, large y derivative, where the value of our large y is given by y of x plus epsilon eta of x, and our y derivative is given by y derivative of x plus epsilon eta derivative of x. Now if you're unsure of this stuff here about adding on the variation, again look at the derivation of the Euler-Lagrange equation in the beginning of this video series, or alternatively you can have a look at the first few videos of the first video series on the calculus of variations. So this is really should be a bit of revision if you've done the first course. So we've got the left hand side here of this Taylor expansion for a functional. Now the right hand side is going to be again epsilon times this thing here, which is in this case up here it's f derivative of x, and in this case here it's going to be epsilon squared upon 2 factorial times whatever's in this, which is the f double derivative of x. So we're looking really for these terms here, the f dash of x and the f double dash of x. So we can start off by finding the f dash of x and then differentiating it again to get the f double dash of x. So let's have a look here. We can see here if we were to differentiate partial y by partial epsilon, we get our eta of x. And partial y derivative by partial epsilon gives us eta derivative of x. Again, this is revision, and check out the derivation of the Euler-Lagrange equation in the video series at the video at the very beginning of the series. Now let's say, for example, we say that the value I is going to be given by the functional plus the variation, which is f of x, large y derivative. Then what we want to do is we want to differentiate that with respect to epsilon, and we actually want to differentiate it twice. Okay, so if we differentiate that once, we'll get this term here, and if we differentiate it twice, we're going to get the second term. Okay, so the second term here will be the second order variation of a functional, which is what we're looking to find. But let's find the first order variation of a functional first of all. So we're going to differentiate this once. So in order to differentiate this, you're going to have to use the chain rule. So we're going to have partial f by partial y times partial y by partial epsilon plus partial f by partial y derivative times partial y derivative by partial epsilon. But we know that the partial y by partial epsilon from above is given by eta of x. So we can replace that by, we'll just leave it as eta because we know eta is a function of x, okay? So it's understood. And we're going to have the other value here, which is partial y derivative by partial epsilon, and it's going to be given by eta derivative of x. So that's just going to be our eta derivative. So this little form here, this is our, in effect, our f derivative of x for our Taylor expansion. So again, we've seen this whenever we derived the Euler-Lagrange equation, and we used this with the multiplication of eta in order to work through to get the Euler-Lagrange equation. But what we want to do is we want to now take this here and we want to differentiate it once more. So let's go ahead and we'll differentiate it a second time, and this will give us our second order variation of our functional. So on the previous page we found the first derivative of our functional, so that's di by d epsilon, and we got this value here. So what we'll do is we'll call this first derivative the equation number 1. Now what we want to do is we want to differentiate this yet again in order to get the second derivative. So the second derivative is going to be d squared I by d epsilon squared. So what you're going to do is you're going to differentiate the value for our function again. So you're going to have our partial by partial y of our new function. Well, our new function here is this function here, which has already been differentiated, which is this section. Okay, so it's going to be partial by partial y of number 1, equation number 1, times what we've got left over, partial y by partial epsilon. And then the second term is going to be the partial by partial y derivative of our function here, which has already been differentiated to give us this. So again, that's just number 1 times what we've got left over, partial y derivative by partial epsilon. So this is what we're wanting to do. This is the differentiation that we're going to do. So let's work through the first part with this, and what we'll do is we'll differentiate first of all with respect to y. That's this term here, and then we'll go on the next page and we'll differentiate with respect to y derivative. So everything we see below here is this part of the differentiation here. So let's go ahead and we'll do this now. So we're going to do partial by partial y of 1 above. So we're putting this here into number 1. So you can go ahead if you want and get a piece of paper and actually write that down, and you can stick this inside and you can follow through the differentiation if it helps. But we're going to have our partial by partial y of partial f by partial y. So that's going to give us our partial squared f of partial y squared. So y and y will give us the y squared. So that's the partial squared f by partial y squared. And we're going to multiply it by the value over eta. That's the value over eta. Now we're going to have to use the product rule for differentiation here because we've got a product of two terms. This term here, partial f by partial y, and the term eta. So this has done the first part of the product rule. So the second part of the product rule is we'll differentiate the value of eta with respect to y. So we're going to have our partial eta by partial y, and we multiply it with what's left over, which is our partial f by partial y. That's our partial f by partial y here. And finally, once we've done that, we're multiplying it by our partial y by partial epsilon. So this term here is the first part of our differentiation with respect to x, and that's us done the differentiation of this little section here. So let's go ahead and we'll do the differentiation of this section here in the same manner. We've got the product of two functions, so there's the function here, and then there's the second function. So we differentiate one, multiply it by the other, and then we differentiate the other one and multiply it by this one. So it's just simply the product rule for differentiation. So we're going to have our partial by partial y over partial f by partial y derivative. So that's going to give us our partial squared f partial y by partial y derivative, and we multiply it with our eta derivative. And then we differentiate the eta derivative with our partial y, so we get our partial eta derivative by partial y, and we multiply it with what's left over, which is our partial f by partial y derivative. And finally it all gets multiplied by partial y by partial epsilon. So we're left with this form here. Now we can simplify this quite a bit if we note that the value of our eta, eta is a function that we get to choose, and it's a function of x. Eta is not a function of the value of y. Therefore, we can say that the partial eta by partial y is going to be 0 because there's no functional dependence of eta and y. So that means that we can take one of the terms here and we can get rid of it. So our partial eta by partial y is 0. So this term here becomes 0. Disappears. So we're only left with this part here of this one. Now the next value here, eta derivative, well, it's a function again of x, it's not a function of y. So it means that with the partial eta derivative by partial y is equal to 0. So this term here, partial eta derivative by partial y, this term here disappears. So we're going to be left with this times this one here, and this times this one here. But we know that partial y by partial epsilon is nothing other than our value of eta. So this thing here is simply our eta, and this thing here is simply our eta. So that means that we can then write that as partial squared f by partial y squared times eta times this eta here is going to give us eta squared. And this second term here is going to be partial squared f by partial y derivative times our eta derivative times our eta. So this is simplified. So that's us done 1/2 of this differentiation. We've done it with respect to y. So now we're going to do the second part here, which is this part, which is differentiating it with respect to y derivative. So let's look at that on the next page. So I've rewritten the first derivative of our functional up here. That's the same as the previous page. We're looking to find the second derivative, and we know the second derivative is written like this. We've already worked out the second derivative with respect to y. Now we're going to do the second derivative with respect to y derivative. So we're going to differentiate with respect to y derivative. So we want to do this here, and the value 1 is this function here. So we're putting this inside the bracket and we're doing the differentiation. So let's work through that now. We're going to have our partial by partial y derivative over function with respect to partial y. So that's going to be partial squared f by partial y derivative by partial y, and we multiply it by our function eta. So that's this term here. And again, it's the chain rule, so it's the product rule because we've got a product of two functions. So now we're going to differentiate the eta with respect to y derivative and multiply it by the partial f by partial y. So that's the partial eta by partial y derivative, and we multiply by the partial f by partial y. And finally, we're going to multiply what we have here with the partial y derivative by partial epsilon. So that's the partial y derivative by partial epsilon. So that's just done one part of it. So let's move on and we'll do the same, and we'll do the same for this part here. So we're going to have partial by partial y over partial f by partial by partial y derivative over partial f by partial y derivative. So that's going to give us partial squared f by partial y derivative squared. So that's a partial squared f by partial y derivative squared. And again, we're multiplying it by our eta derivative. Now we're going to multiply the eta derivative. We're going to differentiate the eta derivative and we'll multiply it by this. So this is just again the product rule for our differentiation. So we're going to have our partial eta derivative by partial y derivative times our partial f by partial y derivative. And that's all times our partial y derivative by partial epsilon. So that's us this term here. Now again, the eta is a function of x, it's not a function of y derivative. So we can therefore say that the partial eta by partial y derivative equals 0. And also the eta derivative is a function again of x, not of y derivative. So therefore we can write partial eta derivative by partial y derivative is equal to 0. So it means that we can get rid of a couple of the terms here again. So let's scrub out the ones that we don't need. So we're going to have partial eta by partial y derivative. So that there is 0. So that means that this whole term here will disappear. Okay, so that term there is going to disappear. And we're going to have our partial eta derivative by partial y derivative is 0. So this term here is going to disappear. Also, we already know that partial y derivative by partial epsilon is nothing other than our eta derivative. And we know that our partial y derivative by partial epsilon is nothing other than our eta derivative. So it means that we can multiply these out. So we're going to have our partial squared f partial y derivative partial y times eta derivative. So that's this term here. And we're going to have our partial squared f partial y derivative squared times eta derivative gives us our eta derivative squared. So that's us got these two terms here. So let's gather all our four terms together and we'll again look at it. We'll simplify it and we'll look at the final second variation of our functional, second derivative of our functional. So we can gather together the two differentiations. The one here on the left is with respect to y, and this lot here is with respect to y derivative. Notice that this one and this one are the same, so we're going to finally end up with one term for this. We'll have one term for these and one term for this one here, and we can see that's what we've got down below. Now to note here, whenever the value of our epsilon tends towards 0, the large y of x will tend towards small y of x, and large y derivative of x will tend towards small y derivative of x. So really what we're saying is this epsilon tends towards 0, the variation term tends towards 0, and the functional with the variation added just tends towards the original functional. So we're going to be left with this term here, which is this one, and we're going to have this term here, which is this one, and two of these terms, which is this term here. So this is what we've been working towards over the last half an hour or so. Now just to finish off, what we want to do is we want to take this here, and we also want to take the first variation and we want to put it into our Taylor series expansion. So remember, our Taylor series expansion looked like this. We're going to have our functional with the variation added minus the functional, and it's going to be equivalent to the first part of the Taylor series expansion, which is in effect would be the first variation, and the second part of the Taylor series expansion, which would be the second variation which we're looking at. So let's go ahead and we'll put the values in and we'll get this final result. So we said that our value of I is the f of the functional here, x, y, y derivative. So I've written out the whole functional out with the integral sign as well. And we said that the I plus some delta I is going to be the functional plus the variation, which is the f of x large y derivative. So we could find the delta I here. Okay, so this is in effect the change in the functional, and the change in the function is going to be this minus this. Okay, so we'll just take the common integral sign out. So the change in the functional is going to be this here. And we know that the first part of this, the delta I1, is going to be the epsilon times the partial f by partial y eta plus partial f by partial y derivative times eta derivative. So we got that whenever we looked at deriving the Euler-Lagrange equation, and this was the first part of our variation. And now what we've done is we've derived the second part of this Taylor series expansion, which is given by epsilon squared upon 2 factorial times the integral from a to b of what we've just derived in this video here. So this has us got access to the two things in its essence that we had originally been looking for. We've got our first variation and we've got our second variation. So the first variation is going to tell us whether an extremum exists, but somewhere within this second variation it'll tell us what type of extremum it is. So this is providing us with the necessary conditions for an extremum, and this is providing us with the sufficient conditions that will tell us whether we've got a local maximum or a local minimum. And we want to try and work with this over the next video and see how we can work out from this equation here whether it's a local maximum or a local minimum. So there's a lot involved in that and a lot of maths in it, so take your time to get through it. If you're stuck with any of it, just get in contact and I'll talk you through it. So thank you for listening. I'll get you on the next video. Goodbye.